Hi, I'm Xinren Chen, Associate Professor in International Health Program and Institute of Public Health at the National Yangming Jiao Tong University. We are going to talk about the age-period-cohort analysis in epidemiology. Nowadays, many countries on the world are experiencing a rapid socio-economic improvements, and the disease distribution is also shifting from infection and famine-related diseases to non-communicable diseases like cancer and cardiovascular diseases. We can expect that, like many economically advanced countries, the world population will experience more degenerative disease and man-made diseases like accidents and injuries and mental illnesses in the near future. During these periods of rapid environmental changes, birth cohorts are shaped by the different socio-economical and historical epidemiological contexts when they grow up and age. Therefore, cohorts born in different years would have very different patterns of health risks in their life courses. For example, the children born under different food environments could experience a very different intrauterine nutritional environments, and thus the birth status and birth outcomes could vary by cohorts. Or under the different political economy contexts, the work-related stress rises and changes the health risks to the level that was not ever experienced in the previous generations. So in population, health risks is affected by age, by environments which changes with time periods and also varied by birth cohorts. To tease out the age period and cohort effects on the changing disease distribution in population will provide us important information and understanding on finding the vulnerable populations and to find effective preventive approaches. So let us look at the secular trends of lung cancer mortality. We can see on the graph, the lung cancer mortality increases from 1970s to 1980s and followed by a reduction. This is a pattern in men. On the contrary, in women, the lung cancer mortality gradually increasing from 1970s to 1990s and followed by a plateau in the past decades. Then let's look deeper on the graph to see the age trend by different time periods. And we can see that for the earlier periods, the time trends of lung cancer mortality increased in men from the young age to about 70 years old, and followed by the reduction when they're older. These age trends is heightened for the more recent time periods, so as for the woman's disease patterns. We can present the data of lung cancer mortality in this table. We call it as age by time periods tabulation. The column-wide data shows the age trends for every different periods of years. The row-wise data shows how the disease will change over time for every different age groups. And in these kinds of data, we can even find some hidden trajectory for birth cohorts. If you pay attention on the diagonal cells, the numbers listed on the diagonal numbers which shows how the lung cancer mortality changes over the years for a particular birth cohort. Like the red one, the red numbers shows how the lung cancer mortality increases for the cohort of 1960. And the blue number shows the age trajectory of lung cancer mortality for the birth cohort of 1930. We can illustrate the cohort effects using this graph. In the age by time tabulation, we can see that the shaded diagonal cells is actually revealing the cohort's effects, how the disease change over time for a particular birth cohort. We can also use another way to connect the dots to reveal how the birth cohorts will have different life trajectories of disease risks. As you can see, the dashed lines shows the age trajectory of lung cancer for different birth cohorts. Let's pay attention on the data for the age above 80 years old. You can see that for the cohorts of 1890, the disease risk, lung cancer mortality, was the lowest. However, for the cohort, for example, cohort 1920, the lung cancer mortality was much higher than the older cohorts. However, if we look at the trend, then you can see that the cohort of 1890, the mortality increased after 80 years old. However, for the cohort of 1920, the trend was going down. What we have seen was a graphical exploration of age-period-cohort differences. After that exploration, we will want to know how age, period, and cohort effects are quantitatively affect the population disease risk distribution. So usually we will use a generalized linear model to estimate the age, period, cohort effects. As you can see on the equation, it is a linear additive effect of age, period, and cohort effects on the transformed disease risks. The transformation link function could be log linear, Poisson, and logit functions. As we have seen earlier, based on the age by time tabulation, we saw that the diagonal cells delineate the cohort trajectory over time. And this actually tells us that there's a mathematical relationship across age, periods, and cohorts, as we can see in this mathematical equation. We can calculate a person's birth year by subjecting the calendar year when he is living and the age at the year. And this perfect calculation, mathematical association, will cause an identification problem in the age-period cohort model specification. It is also called a perfect collinearity, which caused an inability to estimate the parameters we are of interest. There have been several solutions proposed to solve these problems, including the reduced two-factor model, a constrained generalized linear model, nonlinear parametric transformation, or finding the proxy variables for the cohorts, and a recently developed generalized linear mixed models. And these models have been used to solve the issue of identification problem. And today we are going to cover a couple of these. First is about the reduced two-factor model. The idea of this model is simple. Just drop the cohort effects, the parameters for cohorts, from the model. However, these kinds of two-factor models assumes there is no cohort effects in the distribution of disease in the population. Therefore, this strong assumption is actually lose the beauty of the original specification of age-period-cohort model, which help us to capture the cohort differences or cohort effects in the population. The most commonly used methods to solve the issue of identification problem is the constraint generalized linear model. It's also called the constraint parameter approach. By this approach, the model will force equal parameters or equal size of effects for two adjacent groups. For example, two adjacent age groups or two adjacent time periods. By using this, it will free some degree of freedom for the statistical model to estimate the parameters of interest. However, these kinds of constraints need some external or side information to help us to decide what factors or what effects to be constrained on. And the choice of different constraints in the APC model could affect the final results of estimation. Let's take a look of an example. This example shows the mortality rates in women in the United States from the 1960s to 1990s. And the graph shows the age trend of mortality for different time periods. And based on this data, we can estimate the age, periods, and cohort effects of mortality in women. As the figures, the three figures, we can see that the age effects, cohort effects, and period effects has very different solutions or different results when we have different constraint specifications. For example, the model 7, 8, and 9 were constraints on 2 youngest age groups, 2 earliest periods groups, and 2 youngest cohort groups respectively. And then you can see on the graph the trends or the effects of age, the effects of periods, and effects of cohorts will vary when the constraints are different. So you may want to ask, how do we decide a better constraints for the model estimation? Usually we can look at the pure or crude effect models, like the model 1, 2, and 3. And as you can see on the graph, the effects of age, effect of periods, and effect of cohort on the pure or crude models. Only the period effect shows no difference across the years, which means that constraining time periods effects or time periods parameters would be a better choice to diminish the possibility of variation in the statistical differences. This kind of constrained generalized linear model is based on aggregated data, which means that we used the already summarized health statistics like mortality for different age, periods, and cohort groups to estimate the effects of A, P, and C. When there are more and more micro data available or individual level data available, like repeated cross-sectional surveys in many countries, we are having more and more data to explore the possibility of age, period, and cohort effects. As you can imagine, the age effect is individual aging trend, is individual level tendency to have a disease risk. And cohorts and periods are the upper level factors that reflect the environmental effects on individuals' growth or aging process. So it is pretty reasonable to think about using mixed effect model to model the age, period, and cohort effects in the population health risks. As you can see in the equation, the individual level model specifies the polynomial relationship between age and an outcome. For example, we are going to look at the outcome of obesity status. And then followed by population random effects. One is a cohort effect, the other is period or time effects. And using the United States nutritional survey data, it is a repeated cross-sectional survey data. And then we can estimate the effects of aging and the effects of cohort and time periods over the years. As you can see in the table, the polynomial relationship between age and the risk of obesity is significant. And it shows that the risk of obesity is increasing over the age, and it could reduce a little bit in the older ages. When looking at the cohort effects, the estimate shows that there is no difference across the cohorts, which means that actually the obesity risk doesn't show differences across different birth cohorts from 1899 to 1980. Looking at the random effects, the result shows a drastically changes over the time. The risk of obesity increased from the year 1970s to 1990s. And after 1990s, the prevalence or the risk of obesity was stayed at the plateau. So in this way, we can dissect the age periods and cohort effects on obesity prevalence in the United States, showing that maybe the most important issue is the environmental changes over the time, especially during the 1970s to 80s, which causes the epidemic of obesity in the United States. To sum up, these methods can help us to tease out the age effects, cohort effects, and period effects in the distribution of disease in the population. And today, we show you the two common methods to tease out these three effects on the disease. For aggregate data, we can use the constraint generalized linear model by constraining a couple of parameters. But when doing these methods, you should be careful about looking at the original data or the pure, crude effects of age, period, and cohort to determine which effects to be constrained on. If we have individual or micro data available, then we can think about using generalized linear mixed effect models that can help us to avoid identification problems and to estimate the age trajectory of individual under the cohort effects and the time period effects. After the class today, we hope you are interested in doing age-period-cohort methods and start to think about how to use this method on your own data. The method is actually evolving still. So if you are interested in this topic, you can go to the reference book we put here. And of course, if you have questions, and you are welcome to contact us, we can discuss more in the future.